Okay, so we are going to get deeper into this. So we need to compute the integrals, and again this are, you see that you know quite a bit of what is being done, but it is done in a nice way for many variables. These integrals are, there is standard way to do this in integrals, and you can get pretty nice interesting results. Okay, so we will go further into how to compute the integrals. So far was only formalism. I said, well, the partition function is there, but we need to compute the partition function for many for example, there are many spins either in real space or Fourier space, then I need to compute the integrals, and that can be quite tricky. So let us try to use it. Also Feynman path integral, though the formula is pretty nice, that it sum over all paths e to power minus s by h bar, I sum it up, but summing up it is pretty complicated, no. So, but we need to do it if you want to get some quantitative numbers. So let us do some of these integrals, and as I said, field theory involves lots of integrals. So that was my remark in very early times, and it is true, there will be a lot of integrals. Okay. So let us look review quantum Feynman path integral. So classically, for classical particles we compute action, no, which is Lagrangian of this particle, well, q dot, I should have put q dot. So position and velocity, and we do the compute the action, this called action, no, S is action, and which is integral dt from A to B. Okay, I go from here to there, and what classical physics tells us, that the trajectory chosen by classical physics is the one which extremizes S, mostly minimum, but sometimes is a maximum as well. But in quantum mechanics, particle does not follow classical trajectory. In fact, there is no particle, but we can get a pretty nice picture of the probability amplitude by following this analogy. So electron is going from A to B, but we can compute, we can't say which path it goes through, but we can say probability amplitude from going to go from A at time t1 to B at time t2, we can get the amplitude, and this is what is this well, what Feynman said, that it follows all paths, but each path has certain weight, and you sum it up, and that will give you the probability amplitude, which is the Green's function. Okay, our connection is the Green's function. So it is a time dependent Green's function. So q1 t1, which is the starting time and starting position, to q2 t2, and this is the Green's function. It is a starting position qa to qb. So the starting position at a time ta, and final position is qb at time tb, but it follows all possible paths, and here it has been discretized. You take various snapshots. This trajectory seems pretty vague, right? I mean, particle is its derivatives are not defined, non-differential, right? I mean, this is like cusp here, but this is allowed in Feynman path, in Feynman's calculation. All paths are allowed. It should be continuous. That is what it is. There can't be a jump, and there are ways to think of antiparticle as well, but we are not doing it. Just think of particles, and whether sometimes particle is going back in time. Well, here is all going forward in time, but things can go back in time. That is also allowed in path integral. So this is so e to power I s by h bar. This is the amplitude for a given path, probability amplitude, and you sum up over all paths. Okay. So this integral, no, I mean this integral, and this dq is a functional integral, right. So q is a function. Well, q is basically here this g is function of q, and but q itself is varying. So remember we had started with functional. So I is function of f. So my integral is function of f, which can be any function. So my q is an arbitrary function, which can be non differentiable as well. Okay. Anyway, so this is a prescription. Now, point is how to compute this. This requires pretty complicated integrals. It is possible to do it analytically for some standard potentials. I am going to show one potential. Well, I am not going to do it, but it's you can find references and you can do that. I am just going to show you how to compute for free particle and mention about the procedure for oscillator. Again, you can look at this book, Lister and Blundell. Okay, some overall pass. That's a difficult part you need to compute. So some integrals. Okay, now these integrals will come quite often. So this is a Gaussian integral, right? It's ax squared by 2. A is a real number, positive real number. Okay, and the answer is square root 2 pi by a, minus infinity to plus infinity. Yeah? Now bx, the b is a source term. Huh? So this is a nice. So for this is 1D and one variable x. So b is a source term, no. So I had the integral e to power minus beta h. H could be x squared, no, plus source term jx. That's what I had in the past few slides. So and this is somewhat all possible x. So this is dx. So for a particle in a thermodynamic particle in a chamber, so this would be the Vx could be velocity half v square and j times v. Okay, now we can think of that as a some force connected with velocity. Okay, so x is a variable. Now, so what is the integral for this? We can this is you can bring it to quadratic form. You need to bring it this form. So change the variable. So I say x minus b by a whole squared. So this part is, and of course I need to correct it because I am adding something here. So correction is this, add subtract. Okay, I am sure you have done this, but if you add subtract and bring it to exponential form. So this part I can use this formula, and this part is constant, right? It is not function of x. So this is straightforward, e to power b squared by 2a square root 2 pi by a. Okay, so this is coming straight from this one, this middle part. Now let us make it more complicated. Well, I am just rewritten it now. X squared by 2 is so bx. Now what we will do is we will make this A is a matrix. So I need to bring in many variables. So what should I do? So let us just get the idea here, dx1 dx2. So we have x1 and x2. So here instead of x squared I will have various combination. No? What combinations will I have? Exponential. So we will have x squared, x1 s squared, x2 squared, plus it is all minus, plus x1 x2, and there will be coefficients in front. So a, b, c. It looks pretty complicated, but you can write this in terms of matrix. It is a quadratic, no? So quadratic can always be computed into the matrix. So what is the trick? We put a matrix A, x1 x2 and x1 x2. Now I am going to pull this coefficients of A. Now x1 x2 is symmetric. So in fact we know how to do this one. What should be A? So the first diagonal element will be small a, right? This one. So x1 x1 will become a squared. These guys should be b, and what should be the off diagonal terms? C by 2, C by 2. Okay. So that is how we should write. For n variables we can always construct this matrix A. It is complicated, no doubt, but it is possible to do it. Okay, and this is going to be symmetric matrix. Okay, now that is how. So if there is a matrix, then how do I compute this integral? Okay, so that is the next slide. So we write this in terms of matrix xi, aij, xj. I showed you for 2 by 2, but we can do it. Now, this is proven. We can look at the standard probability theory book. Okay. This Gaussian is very important probability distribution. No? Why is Gaussian important? It turns out if you have n independent variables, okay, n real independent variables, and they are interacting, well, I mean, but they are independent. So, well, let us say think independent variables, and probability distribution of n independent variables is Gaussian. So, that is why the particle distribution for in a thermodynamic gas, it is Gaussian, because they are not interacting, and they are colliding, but they are not, that is how it is randomizing, but they are not interacting per se, there is no correlation between the particles. Okay. So, that is the central limit theorem. So, exponential is the Gaussian is a very important distribution, which is comes in all places. Non interacting typically will be Gaussian. Okay. So, this is my this I will see it for n variables. In fact, we will see it soon in our course. Now, this integral, well, one thing is to diagonalize it, right? The idea is to diagonalize it. So, once you diagonalize it, is going to be e to the power half x tilde 1 squared. In diagonal form, it will be x1 tilde square, x2 tilde square, and sorry, lambda eigenvalue lambda 1, right? That is how diagonal things are. I mean, this linear algebra comes into play here. So, lambda 1 x1 square plus lambda 2 x2 square, and so on, and each of them are independent Gaussians. So, we will get if I do the integral, I will get lambda 1, lambda 2, lambda 3, all that square root below. This a will become lambda 1, lambda 2, lambda 3, and so on. So, this is what we are getting 2 pi n 2 to the 2 pi to the power n by 2, which is from here, and this a is replaced by eigenvalues, which is determinant of a. Okay. So, interesting. So, n variables we can also compute the integral. Now, we will also encounter cases when we have source term. By the way, this we can write in terms of x transpose A x. X is a vector and A is a matrix. Now, the source term we write as B transpose x. Okay, so, this is like this and like that, and we just follow the same scheme what we did here. Then we will get this term is translated to this form. It is quite nice. Now, B is B transpose, 1 by A is A inverse, and this B is B. Okay, so, and this determinant A remains as is. Okay. Now, we will also encounter situation when we have this integral, divide this by minus infinity to infinity dx1 and da 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 dxn exponential minus half xt a x. So, what will I get? I divide this divide by that. So, this guy will get cancelled, and I will get just this. Okay. So, this is a we will see this kind of stuff. So, this is a full partition function with interaction. So, this guy will be like a source term, and this will be free Green's function, a free partition function without source. This one is with source and this one without source. If you do the ratio, we will get only this exponential part. Okay. Now, so once you know these formulas, at least have a reference, you can keep it with you, and then you can compute a lot of integrals. Now, that was for x1, x2, x3 and so on, right, but and my A was a matrix. So, that is a discrete variables, but we can have a continuum. Okay. So, this is some continuum operator A x y, and here we need to find A inverse. So, this is very similar to what we did, but this for continuum A. You can't form a matrix, but you have a functional A x y. Okay, it's possible, especially when you have continuum, but it's possible. But we will use discrete for our future discussion. I am going to go to Fourier basis and I am just going to use discrete x1, x2, k1, k2, k3 like that. Okay. Typically that is what I will do. Okay. Now this is for find path integral for oscillator. So these some tricks which we need it, well I am not going to do it, but this in the course I am also going to mention how to do this stuff. So this part is quadratic, no, x squared, but this part is not, I mean q dot is a quadratic in dot, but I want to get rid of these dots, d by dt. So this one is solved by doing a integral by parts. So if you do integral by parts, then this is first function integral of second minus integral of second, well derivative of the first function integral of second. So this is standard trick to convert double to derivative squared to function and double derivative, and source term is 0. So this is now QQ, right, QQ, and this is an operator, linear operator. Okay. So it is a kind of not so convenient looking operator, but it is a linear operator. So I can use now, well basically my operator is this. Okay. So remember I was telling you that I can't write this into the matrix, but it is a function AXY, that is what I wrote there. Okay. So it is a function, and there are ways to compute it. You can look at this book. So this derivation is definitely not easy, but if you follow this path, well how to find the determinant of this operator. Okay, so now that is what is done there in terms of eigenvalues and so on. This is the Green's function or probability amplitude for simple oscillator to go from origin at time t equal to 0 to origin at time t. Okay. Particle does stuff and comes back for a time t. Okay. Derivation I am not doing it here. Okay. Anyway, this is some ideas about path integral. Now let us get to some more complicated operators. Now this is our Klein-Gordon field, right, Lagrangian for Klein-Gordon field. So this is my so I am again, it is like a partition function. Okay, it is a action, actually we will call it action. In quantum mechanics it is called action. Partition function is integral of e to power is by h bar plus is by h bar. Okay. So this is the action. I exponentiate the action. This is like, okay, no sorry, this action, apologies, this action, this is partition generating function. I mean generating function, it is not called partition function, generating function, and d phi exponential. I am doing this, but with a source j phi. Now this square, again we have derivative squared, no. So this is converted to Laplacian to derivative operators. Same trick which I did in the earlier slide. So phi, this one phi, and this is a source term j phi. Okay. Now so what we did for oscillator, we can follow the same procedure. Well, of course this is more complicated integral, and so this j naught z naught j, this is a math cal. It is written as this divided by, I am dividing the so this source term sitting here, and I divide with the one without source term, and this is the integral which in fact I mentioned to you how to do it by these formulas. So this part I bring it down, and basically b divided by a, we are doing b divided by a. That algebra will be more complicated, but basically you do the b divided by a, and that is what it is, right. This exponential b transpose a inverse b, that is what we got here. So this b is, this is b transpose and this is field operator phi. So, this is B, and inverse of this operator is Green's function, right. G inverse was, so we had L G equal to 1 or delta function depends. So, basically G inverse is 1 by L. Okay. So, 1 by Laplacian, this A inverse is coming here, which is nothing but the Green's function, and delta is the Green's function. Feynman propagator, which I derived in the last class. Okay, this is a Feynman propagator. Okay, so you see that there is a underlying math is very similar, and it's all in here. Okay, now once we have this, then I can compute the correlation functions or Green's function by taking derivative with J. I may discuss this before. So, by the correlation function is the most important thing, spin correlations, field correlations, and this is for in real space. Well, this for two point correlation x y, and this is n point correlation. Well, I am just cut paste here, and if you write down this, of course you need to remember this stuff, but okay. Now, this is a slightly tricky part. Now, in quantum field theory, we have integral in space time, right. We have dt dx cube. So, space time t and x are different, but I want to convert it to Euclidean space where all of them are in the same footing. So, we had discussed before that t square minus vector this square is invariant, Lorentz invariant quantity, but I do not like the minus sign, I want a plus sign. So, what should I do? I replace t by minus I tau. So, this change of variable is called weak rotation, this weak rotation, weak is a person, this is so Week's rotation, and so idea is that we are doing the integral in time in the real line like that. So, this is this time, but I want to do it along the complex line. So, I do a rotation, I go down like that, that and that. So, if the integral over this quarter circle is negligible, then this integral and this integral will be the same value, okay, because for analytical function or any loop integral must be 0 in complex plane, okay. So, this is a weak rotation. It turns out that we can convert the Feynman path integrals to a Euclidean integral in where all the 4 coordinates or 4 variables are in the same footing, okay. And in statistical field theory, we do not have time, okay. We are basically doing equilibrium, and we are not thinking about time playing a role. So, get rid of time, and it turns out that lot of formulas which you derive for quantum field theory can be ported here, and especially for statistical quantum statistical mechanics, okay, that these are important framework. So, I am just giving a brief introduction because we are doing all this. So, for completeness I am mentioning this, and as a result I just replace this t by minus I tau, then it becomes, you see this is the same, all of them are added plus plus plus, okay, and this integral, this one is minus I d4 xe. So, it is like dx, dy, dz, dw, standard integral we do in classical mechanics or classical physics. So, this is Minkowski space, Minkowski space. Okay, and my this dt square minus Laplacian becomes plus, right, because this I square will give you minus, so it becomes plus. So, the Euclidean Laplacian, and this is interesting. So, this I h bar by I h t by h bar, this is a Feynman path integral action, and so my I t is minus I tau. Okay. So, and so basically I am replacing I tau by h bar as beta. Well, this is a trick. So, basically I am going to just briefly discuss in the next slide. We are getting rid of the time dimension, okay, by some further trick. So, we do not want to do 4 dimensional integral, we want to do only 3 dimensional integral, and there are complications there. Space time is 4 dimension, these also 4 dimension, but my statistical physics integrals are in 3 dimensions. So, that is the next slide. There is a minus integral. Okay, so yeah, this is the trick. So, this is a picture. In time is assumed that so you make a box, the bottom plane and top plane, okay, is periodic in time. So, I want to get rid of this time part. So, this is the space part which is nice, I can current to it with the minus beta h. Hamiltonian is integrated in 3 space, and this part is periodic. So, with the frequency will come into play. So, a string in a periodic domain that will be oscillating with certain frequencies, and that is how we get rid of this part. Okay. And so, I am just mentioning it here. Tau is finite, 0 to beta, and so basically the time part is eliminated by some tricks. So, d plus 1 space dimension is converted to d dimensional space with time eliminated, and this is possible under certain limits and certain algebra. Okay. And you can again look at this book QFT for gifted amateur. Okay. So, I think I will end about the Feynman path integral at this point. Maybe, but we need some of these formulas for our future. Any questions on this? Well, of course, this was mostly math, except the last part which is not easy. So, the connecting field theory with statistical field theory, that part is tricky, which I do not understand fully either. So, we need to do the computation, then only we will understand it. So, I have not done it. So, but I think you need to go back and look at your notes.